This, in my textbook, is chapter 9. In your textbook, it's sections 9.4 through 9.8. All right. I'm going to shrink that some. Yeah. Get that out of the way. There we go. Okay. So let's finish off our discussion of orbitals. And we're going to focus on covalent bonding. So we're essentially finished with ionic bonding now, and we're only talking about covalent bonding. So when we left off with the VSEPR model, we were able to predict the geometry of a molecule based upon the electron groups that surrounded a central atom. And if we do methane and we write the Lewis dot structure, we find out that it has 4 groups around the carbon, which makes it tetrahedral. And the bond angles are 109.5 degrees. All right, so the problem is with methane, if we're talking about the central atom, remember carbon has an electronic structure. And remember, the valence bond theory and the localized electron model says that the electrons still belong to each atom, and they just share them by overlapping orbitals in order to form the bonds. So we have to work with the electronic structure of each atom. Hydrogens are easy. They're just 1s1s, right? All 4 of those hydrogens. The carbon, however, is 1, 2, 3, 4, 6, has 6 electrons. 1s2, 2s2, and 2p2. So the bonding is only going to take place, according to the valence bond theory, with the valence electrons. So we only have to concern ourselves with the valence shells. And notice we've got 2 electrons in the s orbital and 2 electrons in the p orbital. If methane is going to be a symmetrical tetrahedral geometry, then the bonding between the carbon and each of the hydrogens has to be identical in order to do what we expect it to do. Like that. Well, that's not a good one. Like that. So we're going to have a hydrogen back here, hydrogen there, hydrogen here, and a hydrogen there, and then carbon up here somewhere. So we form these bonds. And each of those bonds must be equivalent. I mean, the experimental evidence says that they are. And the shape of the molecule is based upon the tetrahedron. Well, you can't get that from 2 s's and 2 p's, right? Because the p orbitals are going to be like that, right? And we're only going to use 2 of them. So, but the s orbitals are like that, right? You can't get a tetrahedral structure out of that. This is where the valence bond theory falls apart, because it says that these electrons belong to carbon and those electrons belong to hydrogen. If they're going to overlap, then you cannot change this electronic geometry to suit yourself, unless you introduce a modification, which is what we're going to do next. Okay. So there's a valence electron structure for carbon. And that's why we can't get a tetrahedral structure out of that electronic structure from carbon. So, experimental evidence shows that this molecule is tetrahedral. That's definite. There's no doubt about that. Right? So, we've got to modify our theory. If we don't throw it out, then we have to modify it to accommodate reality. And that's where the concept of hybridization comes in. So what we're going to do, and this was proposed by Linus Pauling. Remember, the same guy that gave us the electronegativity scale, among other things. And he introduced hybridization. Hybridization is a process whereby you take the required valence electrons and their orbitals, and you mix them, and you come out with a new set that satisfies the conditions you need. But those orbitals are still localized on the central atom. Right? So we haven't violated that assumption for the theory. They still belong to carbon, only now, because they've entered into an arrangement with 4 hydrogens, then they had to be modified. Right? So these native orbitals remix, so to speak, and they produce out of 1s and 3 p's, they produce a new hybrid orbital called an sp3. Oops, I put the 3 on the wrong place. sp3. Now, the number of hybrid orbitals has to equal the number of pre-hybrid orbitals that went into their makeup. So we've got, remember, S's, and we've got 3 P's. Right? 1s and 3 P's. Those 4 come out here. Now we have 4 equivalent sp3 hybrid orbitals. And these all point in the proper direction to give us a tetrahedral structure for the methane molecule. Now, in order to do that, let me back up. For elements, we have a quantum mechanical equations that are solved using the 4 quantum numbers. Remember, N, L, M sub L, and M sub S. Those 4 numbers go into the quantum equation and predict both orbital probabilities and energies for the element. But there are also a set of quantum mechanical equations that apply to hybrid orbitals. Okay, and that's beyond me and beyond this course. But I just wanted you to be aware of that. It's not something that Linus Pauling just pulled out of thin air. He was basing it upon the quantum mechanical equations for elements, and then they just had to be modified to predict these orbitals that were derived from these orbitals. Okay, so if you have an sp3 hybridization, that will predict a tetrahedral structure. sp3 hybridization around a central atom gives you tetrahedral structure. Now, when we say tetrahedral, that can apply to lone pairs also. It doesn't have to be all 4 bonds like this for methane. It could also be ammonia, which has a lone pair, right? So the electronic structure will be tetrahedral for this molecule. So 3 of those sp3 hybrid orbitals will be used to make bonds with these 3 hydrogens, and then 1 sp3 orbital is used for the lone pair. This diagram is sort of a semi-quantitative, or actually a qualitative expression of what is the energy level for these hybrid orbitals. Well, if the energy for the p orbitals is at this level and the energy for the s orbitals are at this level, then the hybrid orbitals are going to be somewhere in between. And if you have 3 p orbitals going in and only 1 s orbital, then it stands to reason that the energy of the sp3 hybrid orbitals is going to be up closer to the original p orbitals. And that's what we show here with this position of these orbitals just a little bit below the unhybridized p orbitals, these sp3s. The concept there is weighted average, right? Just like when we're calculating the molecular weight or the molar mass of an element, the atomic mass. It's a weighted average. And this is not an exact calculation, though. That's one of the problems of the valence bond theory, is that it does not predict accurately actual energies for the orbitals. Well, it does, but when you do that, then you lose information on where the electrons might be, right? Because of the Heisenberg uncertainty principle that we discussed earlier. Okay, so this is what the model says the shape should be. So we have this big bulge on one side and a little blimp on the other side, but they point in those tetrahedral directions. There's a bigger picture of it, including the hydrogens. So in this case, you are overlapping orbitals, 1s orbitals from each hydrogen and 1 sp3 orbital from the carbon, 1 for each hydrogen. Now, we can do the same thing, like I showed you, with the ammonia molecule, and the procedure is the same. You have to draw the Lewis dot structure, right? Well, I erased it. Lewis dot structure, and find out how many groups surround the central atom, in this case 4. So 4 says, according to VSEPR, 4 says tetrahedral. That means that the nominal bond angle, in other words, here to here or here to here, the bond angle is 109.5 degrees. But like I've said before, let me see, somebody's chatting. Okay. After the lecture, I'll deal with the exam. Maybe it's still hidden, but I'll be sure it's showing after we finish the lecture. Unless you want to take it right now, in which case I can pause and deal with that. Is that the consensus, or do you want to continue with the lecture? No preference? Okay. So we'll carry on with the lecture. So we write the Lewis structure and we predict the geometry. Come on. Do it this way. There we go. My 2 mice are in competition, so I had to unplug one of them. Determine the arrangement of the electron pairs using the VSEPR model, and then determine the hybrid atomic orbitals that are needed to produce that geometry. And this is the electronic geometry. So we know that it has to be a tetrahedral electronic geometry, and the nominal, in this case, the nominal bond angle is 109.5 degrees. But we know because even with the hybrid orbitals, with these electrons occupying an unbonding position, they tend to balloon, and they put pressure on these other bonds and decrease this to somewhere in the neighborhood of 108 degrees. Okay, I've already talked about those. So we hybridize two S's and two P's to give us sp3 hybridization. Well, actually, we hybridize all the p orbitals and the one s orbital to give us 4 sp3 orbitals. And you can tell how many there are of the hybrid orbitals. You just count up, right? One of these, 3 of those makes 4. So you can tell from the hybrid orbital notation exactly how many you have. Okay, so there's a model of the ammonia molecule with a lone pair in one of the sp3 hybrid orbitals, and the others are occupied in bonding with the hydrogens. Okay, how about more complicated molecules? It's really not that difficult. What you do is you write the structure, right? Just do it like always. If you've got the compound is this, then we say, okay, we have how many valence electrons for carbon? 4 each, so that means 8. And then 4 here. So we have 12 electrons. So carbons go together, and then hydrogens, right? 2, 4, 6, 8, 10. Minus 10 equals 2 electrons. So hydrogen can't take anymore. So we put the 2 electrons on that carbon. And now how do you make an octet for both of them? Well, you take that pair and make a double bond. So there's your Lewis structure. Now we talk about what's the geometry. Well, we don't have any lone pairs around these, so the electronic geometry is going to be the same as the molecular geometry. So we got 1, 2, 3 groups around this one, which means what? Trigonal planar. 3 groups, trigonal planar. And it's the same for both of them. All right, 3 groups around that one, 3 groups around that one. So how do you get, what kind of hybridization? Let's see, there's the shape of the molecule. And the bond angle, if it's trigonal planar, the bond angle has to be 120 degrees, right? Okay. So how do we hybridize in order to give you that structure? You can't use sp3 because sp3 gives you a tetrahedral arrangement. And this is trigonal planar, right? So it has to be a different hybridization. How do we hybridize? If we're working with carbons that have S's and 3 P's, right? How many of those do you need? You really only need 1 of these and 2 of those, right? So we hybridize these and we make an sp2 hybrid, and then there's 1 P, let's call it Z, that's left out. It's not used. So we get this 3 atomic orbitals go into the hybrid orbital, and that makes 3 of these. So you have 1, 2, 3 that are available for that trigonal planar geometry. Okay, 1 P is not used. So while we're here, what is that extra P used for, right? You got a P here, and a P here, and a P here, like that. What is it used for? It's used for the double bond. Like that. That's That's the purpose of this one. These give you the trigonal planar geometry, and then these overlap to give you the double bond. Now, we call these bonds that are on axis with the atoms. So if you have the carbon here and a carbon there, then the electron density is between the atoms. And this is a sigma bond. That's a small letter sigma, Greek letter sigma. And the electron density is on axis. That means there can only be one sigma bond between two atoms. That's all. There's only room for one. But there's room for a pi bond, which is when you overlap those p orbitals, right? Overlap them, they're off axis. And these form the pi bond. That gives you the double bond. Now, obviously, overlapping off axis is a weaker bond. That's why when we were studying bond energies in an earlier chapter, we had a certain bond energy that could be applied to a single bond, but the double bond was stronger because it included both the single and the pi bond, the sigma bond and the pi bond. But it was not double the strength. And it wasn't double the strength because the pi bond itself is weaker than the sigma. Whenever you have a pi bond, you first have to have a sigma bond. You cannot have a pi without a sigma first. Now, when we look at the energy distribution here, the sp2 hybrid is actually a little lower in energy. Right here. It's a little bit lower in energy than the sp3. And then the unused p orbital is at the same energy it was before. Okay, so this is an idea of what it looks like. An sp2 hybridized orbital gives you a symmetry where the orbitals and presumably bonds are directed to the apexes of an equilateral triangle. So that being the case, right, if you go like that and you put, I don't know, a carbon in the middle and a hydrogen and another carbon and then a hydrogen, then the bond angle here, there is going to be 120 degrees, right? Because 120, 120, 120, that's 360 degrees. So that's a no-brainer, actually. All right, and this is what it would look like. They're on the same plane. All these hybridized orbitals are in the same plane here, right, on the XY plane. And then the unused p orbital is going to stick up to the z and the z, and that's where you get the overlap for the pi bond. So you may notice a pattern emerging, and this would be a good place to start. If we have the number of pairs of electrons around a central atom, and we've talked about 4 at this point, that's going to be an electronic structure of tetrahedron, right? And bond angles are going to be 109.5 degrees. Oops. There we go. Now, what we And you've seen this chart before because we did one for the VSEPR. But what now we're going to do is say, all right, what are the hybrid orbitals that make this possible? Let's see. Hybridization. This has to be an sp3 hybridization in order to give you that geometry. And then we just looked at the one where we have 3 pairs around the carbon, and that's trigonal planar. And the bond angles are all 120 degrees, and the hybridization is sp. Okay? And this diagram shows you the unused p orbitals that then overlap. It's kind of faint, but they're overlapping to produce the pi bond. How about carbon dioxide? Let's use that as an example. So if we've got carbon dioxide, there are 4 electrons here, and there are 12 here, right? 2 times 6 is 12, so we have 16 electrons. Okay, so we put carbon in the middle, oxygen's out here. We're drawing the Lewis dot structure. So that's 2, 4 equals 12 electrons. So then we put 2, 4, 6, 8, 10, 12. So we've used them all up. Now we got to make an octet around carbon. So we're going to be symmetrical about this. We're not going to argue whether it should be 3 triple bond on that side and a single on this side. We're going to make a double on this side and a double on this side. So now we have this arrangement. Okay, everybody's got an octet. And what's the arrangement here? That's linear. We have 2 effective pairs of electrons, or 2 groups, and this is linear. And the bond angle is 180 degrees. Right? The bond angle here goes like that, 180 degrees. Okay, so what kind of hybridization? What kind of hybridization do you need here? Well, you only need 2 equivalent orbitals, 2 equivalent hybrid orbitals to get that to work. So you just hybridize one of the S's and one of the P's. And we have 2 unused P's. Okay? So this is sp hybridization. And with the unused p orbitals, you've got a p going this way, and you've got one going into the back and out like that. So you use these unused p orbitals to make double bonds. Double bond on one side and double bond on the other side. But that also begs the question, what about oxygen? What's the electronic geometry for oxygen? Well, look, it's got 1, 2, 3 groups. That means trigonal planar electronic geometry around each oxygen. And the oxygen has to hybridize to produce sp2 hybrid orbitals. One of them is used for this sigma bond on each side. And then the other 2 are filled with lone pairs. So sp2 hybridization for the oxygen and sp hybridization for the carbon. And now you have a p orbital here and one there and one here and one there. Okay, so this one is used for a double bond on this side, and this one is used for a double bond on this side. Okay, now it's kind of messy, but it's true. So we have a linear molecule, and we have a 180-degree bond angle with sp hybridization on the carbon and sp2 hybridization on the oxygens. Okay, so now you see that the hybrid orbitals are even lower in energy than the sp2s, but we still got these unused at the same energy level as their parents. And that's what the quantum equations tell us the orbitals look like. Okay. So notice that the hybridization around the oxygen makes one of the oxygens right angle to the other one. In other words, you can see that the trigonal planar geometry here is in this plane for that oxygen, but it's in this plane for that oxygen. So the unused p orbitals are here right angles to each other, and they overlap at right angles depending on the p orbitals that are used by the carbon. That's the only way it makes sense. Oh, there we go. So what we're seeing is, and I'll make this point now, when we use the VSEPR theory, you know, I was complaining that it said valence shell electron pair repulsion. And I was saying that doesn't make any sense because we're counting a double bond the same as a triple bond and the same as a single bond. So it should be electron groups. Well, at that point, that was a valid complaint. But now you see that the geometry is not with the pi bonds of the double or the triple. The geometry is established with the sigma bonds. And then the pi bonds come after with unused orbitals. So now that is an accurate statement. VSEPR, valence shell electron pair repulsion. Because it takes one pair to make a bond. All right. So how about the nitrogen molecule, the dinitrogen molecule that we breathe every day? What are we looking at there? Let's see. Yeah, I filled in that one. So let's look at the dinitrogen molecule. All right. 2 nitrogens, 7 valence electrons each. No, 5, excuse me, 5. So that's 10 electrons. So we have nitrogen, nitrogen, minus 2 was 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we need to make an octet for each nitrogen. The only way to do that is to use, let's see, if you make a triple bond here, 2, 4, 6, 8. So that Lewis dot structure is going to be like this with a lone pair on either side. Okay. Now, how many groups around each atom? 2. So that means it's going to be linear. And that means it has to use sp hybridization. So sp hybridization here and sp here gives you a linear structure. And then you've got 2 unused p orbitals on both nitrogens. And those unused p's give us a pi bond here and a pi bond there. So we have a sigma, and we have a pi, and we have a pi. All right. Come on. There we go. All right, so that says in black and white what I just told you. And this is what the artists think it looks like. All right. Now let's get more complicated, right? Because we know with the VSEPR model, we have more than just 3 possibilities, right? Suppose we have 5 effective pairs. And here's an example, PCl5. Right? Phosphorus is 5, and this is 7 times 5. So that's 8 times 5 is 40, 40 electrons. So if we have a phosphorus in the middle, and then we have chlorine at each one of these positions. So 5 times 2 is 10. So we have 30 electrons left over. Six more electrons for each chlorine, and there are 5 of them, makes 30. So they're all used up. Now we have 5 effective pairs, which gives us what structure? A trigonal bipyramid. Okay? A trigonal bipyramid says we have a triangle here, and then we have 2 apexes, one on top of each other. In here we'll have phosphorus, and here we'll have chlorine, 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 and chlorine. Let's see, 1, 2, 3, 4, 5. Okay? So what are the bond angles? Well, around here, in the triangle, it's the same as trigonal planar, 120 degrees. Okay? Between one of these triangle chlorines and an apex chlorine is, let's see, 90 degrees. And then if you have a bond angle between this chlorine with phosphorus at the apex, chlorine, phosphorus, chlorine is 180 degrees. So what kind of hybridization can you conceive of to make that possible? Well, we've used up all of our S's and P's. sp3 won't do it. That's tetrahedron. So we have to go to D's. We have to add in a d orbital. Right? That gives us 3, 4, 5. That gives us 5 hybrid orbitals, which accounts for all of the chlorine atoms bonded to the phosphorus. Now, can we get away with that? I mean, is that permissible? Well, yeah, because phosphorus is in the 3rd period. Remember, n equals 3. That means if n equals 3, that means we have L's equal to 0, 1, and 2, S, P, and D. So phosphorus does have access to a 3D orbital. So we can say DSP3. Don't ask me why the D comes first, because if you go according to energy, SPD should be the last one, but who knows? DSP3 is how we is the nomenclature for that hybrid orbital. Let's see. And that's what it would look like. The chlorines, would have to, let me see, chlorines would have a 3s and 3p. Okay, that one and that one. Right? So chlorine would also have to hybridize in order to produce yeah, but it's not as critical because it only has to overlap one orbital. The real critical part is what do we do with the phosphorus, because it's in the center. All right, we got one more, I think. Right, octahedral. So our example here in the slide is xenon tetrafluoride. Now this is, we're talking about the electronic structure. So in order to draw the Lewis dot structure, we need 8 electrons from xenon because it's a complete octet. And then we need 7 times 4 for fluorine, which equals 36. So xenon is in the middle. And then we have fluorines, 2, 4, 6, 8. So we have 28 electrons that we have to use. Right? 6 times 4 is 24. Equals 4 electrons. The 4 electrons have to go on the xenon. So now if we're counting up groups or pairs to determine its electronic structure, we have actually 6. We have 6 effective pairs, which is what? Octahedral. Okay, so an octahedral structure puts a square in the middle, xenon's here, and then like that. So fluorines are going to be on the square, and the lone pairs are going to be here at the apexes. Okay, so if we form bonds here like that, how are we going to hybridize in order to get 4, 5, 6 hybrid orbitals? Well, xenon is in the 5th period, so it definitely has access to d orbitals. What we need is actually 2 d orbitals. So 3, 4, 5, 6. That gives us 6 equivalent hybrid orbitals. Now, what are the bond angles? Well, let's see. Around the square is 90 degrees. And then, well, that's it, right? For this molecule, it's 90 degrees because we don't have any atoms up here on the apexes. So there are no bond angles there because there are no bonds. So the only possibility for this example is 90 degrees. If you had a molecule where you actually had something up here and something down here, an atom and an atom, then you could possibly refer to a 180 degree bond angle for those 2 apex atoms. But for this one, our example, 90 degrees is all we have. Right? So when I say 180 degrees, that's only for molecules with 6 actual atoms. All right, so that's the D2sp3 hybridization that gives us 6 equivalent hybrid orbitals. And we know that this is valid because experimental evidence says that it's not tetrahedral, but in fact it is square planar. So we have to arrange them that way. All right. Now here's a little table I threw together, and this one's kind of inverted. So this table is in order, right? It goes from 2, 3, 4, 5, 6 all down, and gives you the VSEPR geometry, electronic geometry, and then the hybridization that's required. That needs to be superscripted right there. Okay, I got some work to do on this slide. All right. So let's see if we can make sense of this molecule. Hydrogen cyanide. We've done the Lewis dot structure for this one before, and it's just like that, right? It's got a triple bond here, single bond there, and a lone pair on the nitrogen. So, how many, let's see, I think I've got an animation for this one. So since it's a linear molecule, the hybridization is sp on the carbon. It's also sp on the nitrogen, right? Because it's got a lone pair here and a group on that side. So it's also sp hybridized. And then the unused P's from both of them are used to make two pi bonds. There we go. So there's a sigma bond. There's a sigma bond. Now we can make pi bonds since all the sigmas are taken. Okay. Let's see, bond angles and hybridization for these guys. We've already done ammonia and carbon dioxide. So we'll go to sulfur dioxide. Right. Okay, sulfur and oxygen are in the same family, so they each have 6 valence electrons. So 3 times 6 is 18. Right. Sulfur, got an oxygen, that's 2, 4. And that's 14 electrons. So 2, 4, 6, 8, 10, 11, 2, 4, 6, 8, 10, 12, 14. Okay. So sulfur needs an octet. So it could either get a double bond from this side or a double bond from that side, which would set it up for resonance. We would have 2 equivalent structures that would have to resonate. But we're only going to look at one in this case. So we're going to take those 2, right, and make a double bond here. Here we go. Now, we have an octet here, octet there, octet there. What's the symmetry around the sulfur? Right, we have 3 groups. 3 means trigonal planar and 180-degree bond angle. All right, well, there's the ammonia. And there's the sulfur dioxide, 122. And the hybridization has to be sp2 because you need 3 equivalent orbitals, 1, 2, 3, to accommodate 2 sigma bonds and a lone pair. KRF2. I jumped ahead of that one. All right, let's do it anyway. All right, so there's 8 here, and 2 times 7 is 14, so that's 22 electrons, isn't it? 8, 4, yeah, 22. Okay, krypton, fluorine. I know we're going to have to do this anyway. So that's 2, 4, 6, 8. 2, 4, 6, 8, 16 equals 4, 6 electrons. 2, 4, 6. All right, so around the krypton, we have 1, 2, 3, 4, 5. 5 means trigonal bipyramid. And we've got 3 lone pairs. So where do they go? Well, they go like this. We have, let's see, like that. Lone pairs go on the triangle. The fluorines go at the apex. Right? So the bond angle here is only 180 degrees. But we have 5 effective pairs around the krypton, which means trigonal bipyramid, dsp3 hybridization. We need 5 orbitals. The only way you can get that is one of these. D, S, 3 P's makes 5. Let's see. Next one's probably carbon dioxide. We've done that one already. And then iodine pentachloride. Right? 6 times 7 is 42 electrons. So we have an iodine in the middle, and we have 5 chlorines around it. Right? 2, 4, 6, 8, 10 equals 32 electrons. And if we put 6 around each one of these chlorines, right? 5 times 6 is 30, means 2 electrons left over. So now, around the iodine, we have 1, 2, 3, 4, 5, 6. 6 pairs of electrons, which means octahedral. So we've got an octahedral structure with iodine in the middle. Okay, where does the lone pair go? I think for octahedral, the lone pair tends to be on one of the apexes. Right. Chlorine, 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 and then chlorine, and then a lone pair. So that makes a square pyramid structure. And since we have 6 effective pairs, it's octahedron. And these bond angles are 90 degrees. And these bond angles are 90 degrees. D2sp3 hybridization. Okay? All right. So this just summarizes what we've done. Draw the Lewis dot structure, determine the arrangement by the VSEPR model, and that will tell you what the hybridization is, because this hybridization is specific for each of these electronic structures. These electronic geometries will tell you what that has to be. If you got 6 pairs, it's got to be D2sp3. Can't be anything else. Okay, we're gonna rag on localized electron model now. The model incorrectly assumes that electrons are localized to each of the atoms. These electrons, once you get into a molecule, in fact, those electrons now belong to the molecule. They don't belong to you. It's kind of like communism on a molecular scale. The whole molecule owns the electrons. It also, and I think we have maybe one example in the past, the localized electron model doesn't effectively deal with unpaired electrons. What do you do with free radicals? I mean, we had one, it wasn't nitrate, but it was one of those nitrogen oxygen compounds, I think, that gave us a free radical. And we just had to sort of ignore it. And the model does not provide direct information about bond energies. You can't calculate what the bond energy is based on this model. Okay. If this were a like an hour and a quarter class twice a week, then, or hour and, was it 3/4 maybe, twice a week, then this is where I would pause. But I don't have to pause for this class because we do it one shot every week. So we're going to carry on. Now, here's the solution to the problem. It's called the molecular orbital model, so often abbreviated MO. The difference in this model versus the localized electron model is that the electrons are in fact assumed to belong to the molecule, not to individual atoms. So that being the case, we've got to find places to put them. Right? So mathematically speaking, probabilistically speaking, quantum chemists have derived a set of equations that allow them to calculate both energy and probable shape of orbitals and various other things, actually. For the molecule, once we know the orbitals and electrons that are coming in from atoms and mixing, then we can, out of that, create these molecular orbitals. There are some rules from the atomic orbitals, from the valence shell, the valence bond theory, localized electron model. There are some rules that transfer over and some that don't. So let's go through those. This one comment. We call them orbitals, but they're not really orbitals. Not like planetary orbitals where you have a nucleus and electrons going around in a circle. That's sort of grandfathered in. We're stuck with that terminology. So when we say orbital, we actually mean where is the highest density of electron probability. Right, here's a side-by-side comparison of the localized electron model and the molecular orbital model. Major difference. Localized electron model depends upon atomic orbitals and their interaction with each other between atoms. Whereas the molecular orbital model creates a whole new set of orbitals, molecular orbitals. And when it does, the atomic orbitals from which they were derived disappear. No more atomic orbitals. Now that you're in the molecule, you have a different set of orbitals. We still treat them in a quantum mechanical sense, except that in the localized electron model, the atomic orbitals extend over the molecule as far as they can to create a bond. Whereas in the molecular orbital model, the quantum mechanical solutions to these equations apply to the entire molecule, no matter how big it is. So you can imagine that the bigger the molecule, the more complex the calculations. All right, localized electron model, obviously, the electrons are assumed to be localized to an atom and spend their time between or just off axis of the two bonding atoms. It's like you treat those two atoms as if there's nobody else in the room. It's just me and you, and how do we bond? Whereas the molecular orbital model says all these electrons are delocalized over the entire molecule in this new set of molecular orbitals. And in fact, this delocalization, remember that word, that means can be equated with stability. The more delocalized you can make electrons, the more stable the structure. We still have, I went the wrong direction. We still have 2 electrons per orbital. That hasn't changed. The psi-square wave functions that are part of the quantum mechanical equations are solved for atomic electron probabilities in the localized electron model, and a new set of equations are used to solve the molecular orbital wave functions for the electrons that are in the molecular orbital model. But they're both quantized. In other words, electrons can only occupy atomic orbitals in bonding or molecular orbitals in the new molecule at certain energy levels, and nothing in between. They're either here, 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 wherever the case may be. There's nothing in between. We're still quantized. All right. This rule is chiseled in stone. when you form a molecule, each atom brings to the party a certain number of atomic orbitals. Right? Some of them are core orbitals, some of them are valence orbitals. Those all go into the mix. And the number of molecular orbitals that comes out is exactly equal to the number that went in. So it's kind of like the law of conservation of orbitals, for lack of a better term. All right, I've got a video, actually 3 videos coming up. And the first one's going to talk about interference. And in that one, we treat electrons as if they were waves. That's why the chi-square function is referred to as a wave function. So we treat electrons as if they were waves. And when we do that, then we can discuss them in terms of interference. And that term will be expanded upon in just a minute. So we can also view these orbitals in terms of whether they're on axis or off axis. Sigma orbitals versus pi orbitals. Sigma molecular orbitals, pi molecular orbitals. Right? That has not changed either from the previous discussion of the localized electron model.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when 2 waves travel through each other. Here's a moment when 2 highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the 2 lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the 2 waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
All right, so this concept of interference, constructive interference and destructive interference, is used to determine where the electrons might congregate, might be most probable to locate. And what we've seen is when we draw an atomic orbital, like a p orbital, then we might have something like that. The constructive interference would give you something in this region. The destructive interference will give you a node, or out here where there's no probability of finding the electrons. That works for molecular orbitals also. Except what we were witnessing in this video was a two-dimensional representation of a wave, which is easier for us to wrap our minds around. But in three-dimensional space, this wave interaction is occurring in 3 dimensions. And really, the best way to visualize that is not with a video or with a drawing, but with mathematics. Okay. So what we have witnessed is when these waves approach each other, they are superposed. Superposition is a word that's used for interactions of waves when they overlap. Interference is just a description of what they do when they interact with one another. It can be constructive, which increases the amplitude of the wave, or it can be destructive, which decreases. Now, what we were shown in this video were 2 waves of exactly the same wavelength and amplitude. So when they interacted, you got a fairly easily described increase in height at one point and complete cancellation at the other. But in reality, when 2 waves interact, they don't have to be the same wavelength frequency, for instance, to interact. And when that happens, you get a very complex pattern of constructive and destructive interference. These complex patterns, actually, we use them every day, particularly in our communications. FM radio, for instance. How do we get that information coming out of thin air, so to speak? Well, at the station where the signal is produced before it is broadcast, let's keep it simple, talk radio. So the voice of the speaker is recorded in wave patterns, and then those wave patterns are superposed upon a fixed carrier wave. For the program that I listen to, it's at 101.1 megahertz. So that's frequency, so you can convert that to wavelength if you want. And when it's superposed on that pattern, it produces a very complex wave structure. And that's what's broadcast from the antenna for that radio station. When I receive it, my receiver simply imposes a 101.1 megahertz signal on that incoming signal in such a way that it destructively interferes with that frequency. So what it does is it cancels out that frequency, and what's left is the original signal, the voice. Now, it can get a lot more complex than that, but that's the simplest way to describe it. Okay, so when we form these molecular orbitals, remember one of the primary rules is when you put 2 atomic orbitals together, you have to have 2 molecular orbitals come out of the mix, right? The atomic orbitals are gone, but now you have the same number of molecular orbitals. The way we do that is we impose constructive and destructive interference on that mixing, that combination of wave functions for each of the atomic orbitals. if we get constructive interference, we form what's called a bonding orbital, a bonding molecular orbital, which here is designated MO sub 1. But you can also combine those wave functions in a destructive manner, and then you get an anti-bonding orbital. Now, from the name of each of these, you can probably surmise that the bonding orbitals are the ones you want to form bonds, and the anti-bonding orbitals detract from the possible bonding. So it's a balance between the two. How many bonding orbitals can you form? How many anti-bonding orbitals do you form? And if they're exactly equal, you definitely don't get a bond. All right. So here's another characteristic. The bonding orbital, MO1, is lower in energy than the orbitals from which it was derived. Right? If the s orbitals are, let's see, was that a hydrogen? Excuse me, let me go backwards. Yes, a hydrogen. So a dihydrogen molecule, right? We have these two hydrogens, and we're going to form a molecule in the middle, right? We're bringing to the party a 1s orbital here and a 1s orbital here, and each one has an electron in it. We're going to form, and this is the energy level here. So if they're at an energy level here, then the bonding orbitals, molecular orbital that forms is actually lower in energy than either one of these atomic orbitals. Right? And the anti-bonding is higher in energy. Right? And we designate these for this purpose. This is a sigma, and it's formed from the 1s orbital. And this one is also a sigma, but it's a sigma star. And notice from that previous slide, the bonding orbital is on axis with most of the electron density between the nuclei. The anti-bonding is also on axis, but most of its density is outside of the nuclei with a node in between. So that means, obviously, it's anti-bonding. It's against bonding. It's higher in energy. And we designate that. This tells us where it came from, subscript, and this star tells us it's anti-bonding. If it's got a star or an asterisk next to it, that's anti-bonding. And this is what it would look like on the slide. Now, when we populate, when we move the electrons from the atoms to the molecules, we do so with Hund's rule. Well, the Aufbau principle, you go from lowest energy to highest, filling it up. And Hund's rule is not a problem here because we only have one orbital right here. But if we had multiple orbitals, then we would have to fill them up with a single spin in each one before we could go back and pair them up, right? And we'll do that in a subsequent diagram. But in this case, we just put one here and one there. So maybe it would have been better to write it this way. Right? There's an electron, there's an electron. Now we put them together in that one orbital, and you see that they're both the electrons are in a bonding orbital and there's nothing in the anti-bonding orbital. So we would expect that to produce a stable bond between the atoms, and that's what we see. Let's see. Yeah, that just explains how I derived these particular notations. So when we form molecular orbitals for the bonding and anti-bonding, they can either be sigma or they can be pi. We haven't got to the pi's yet, but they're coming. I think I got another video coming here too. No, not yet. Now, We can write molecular orbital configurations in string them out across the page, just like we did with electronic configurations for atoms, right? Where we have 1s, 2s2, 2p6, 3s2, so forth and so on. You can do that for molecular orbitals too. But in order to do that, you got to know what's their energy relationship, because it's lower energy on the left, increasing energy to the right. So we have to know what's the order before we can do that. Okay, we're just restating the obvious here. I think we're going to show, yeah. So there's your shorthand version. Now, where did that come from? All right, so let's do the fluorine molecule. Let me give myself a little more room here. So the fluorine molecule, you got an atom of fluorine here, an atom of fluorine there, and you have, we're just going to do the valence shells. So we're going to leave out the 1s orbitals, recognizing that they do exist. And they're actually shown in this slide. But we're only going to do the 2s because we've got limited space. So in that case, we only have 7 electrons each here. Right? Okay, so with the 1s down here, what's next? Well, we've got a 2s right there. And we have a 2p. Yeah, a 2p. But we got 3 of them, right? We can have 3 sublevels for 2p's. Okay? For these, when we produce molecular orbitals, it's just like the one before for hydrogen. Right? Now we have a sigma star and a sigma. And this one says it's derived from the 2s, and this is derived from the 2s. So 2 atomic orbitals, 2 molecular orbitals. For this one, we've got a sigma and a sigma star. Let's see, up here somewhere. Sigma star. These are derived from 2p's. But that only uses one of each. Say 1 here and 1 here, it gives you 2 there. What do you do with the others? Well, in this case, the others become pi's from a 2p and a 2p, and pi star from 2p's. Okay, so we got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 orbitals, molecular orbitals from the atomic orbitals. Right? And you can draw these drag lines here to show where they came from. Now, how about the electrons? Well, in the atomic space, we had 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5. Let's see. 1, 2, 3, 4, 5, 6. 1, 2. Oh, there we go. So these have to go in according to the Aufbau principle, lowest energy to highest energy. So we just start putting them in. We got 2, 4, 6, 8, 10, 12, 14 electrons, right? 14 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, Hund's rule. Now we can go back. 9, 10, 11, 12, 13, 14. Okay? We didn't even use this one, right? That's why it is not that sigma 2p star is not anywhere in this arrangement because there are no electrons to fill it, so we just leave it out. Okay? So now we know the order of energy, right? We've got the sigma 1s and the sigma star 1s down here. And then now we're going to pick it up with what we've got on our board. So the sigma 2s has 2 electrons. The sigma 2s, the sigma star 2s has 2. The sigma 2p has 2 electrons. The pi 2p has 2 plus 2 is 4. Right? So we've combined those just like we did with atomic orbitals. And then the pi star 2p has 4 electrons. That's the molecular orbital structure. Orbital language for difluorine. All right. Now, we've talked about up to this point single bonds, double bonds, triple bonds, and those are whole numbers, right? You either got one single bond, you got a single and a sigma and a pi, or a sigma and a 2 pi to give a triple bond. Well, we've got something that's analogous to that in the molecular orbital model called bond order. The difference is that bond order is calculated from this information. Right? We don't just assume that it's a single, a double, or a triple bond. We calculate the bond order to tell us something about the type of bond that's formed. And we calculate it by totaling up the number of bonding electrons, right? Wherever there's no asterisk, we total those up. And then we subtract from those the anti-bonding electrons, the ones with stars, and divide that by 2. That gives you the bond order. So to calculate the bond order for this molecule, we would say, okay, there are 2, 4, 6. Let's see. Wait a minute. 2, 4, 6, 8. 8 bonding electrons, and then 2, 4, 6 anti-bonding electrons divided by 2, and that's equal to 1. So the bond order of difluorine is 1. And that's analogous to saying it has a single bond. And that's exactly what we observe. There's only a single bond between the 2 fluorines. The difference being, the calculation does not have to give us a whole number. It can give you a fraction. Right? So here's the calculation for our dihydrogen atom. It's simple. We have only bonding, so 2 minus 0 divided by 2 is 1. So we have a single bond with a bond order of 1 between the 2 hydrogens, and that's exactly what we see in the laboratory. Now, what would happen if, and I'm going to refer to the slide for this one. What would happen if we added an electron? In other words, we made an H2 minus ion. Does that stabilize? Is it a stronger bond, or do we destabilize the molecule? Well, if we draw the molecular orbital diagram and we place this extra electron where it has to go in the anti-bonding orbital. So 2 minus 1 divided by 2 is 1/2. We have destabilized the molecule. It went from a bond order of 1 to a 1/2. So it's not as stable as the H2 neutral molecule. Okay, we got another video. These videos, they're going to rehash a lot of things that we've already talked about, but at the end, they'll start to introduce new ideas, or somewhere in the middle. Is one of the reasons I kept them in here, even though they take up a lot of time. I think they are helpful. Oops, I went too far. Excuse me. I need to start this one manually.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have two isolated hydrogen atoms. And we know that each isolated hydrogen atom should have one electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when two atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those two 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the two hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these two nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have one more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? If there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the two nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have two more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so two helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. Now, you might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. Electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching, everyone.
Okay. So a new idea was introduced. Actually, 2 new ideas. Let's see. There we go. Which I'm going to come to in just a minute. But first, I want to emphasize that up to this point, we've been discussing homonuclear diatomic molecules. That is, 2 atoms in the molecule. They're both exactly the same element. Those are fairly simple to construct with a molecular orbital model. But it also means that their bonds are nonpolar. Excuse me. So this concept of paramagnetism, where the our example is liquid oxygen is poured into a magnetic field and is held there in the magnetic field, is due to the fact that there are unpaired electrons. Think of an electron as like a spinning magnet. So you got this sphere, and it's spinning around like that with its pole here, and it produces a magnetic moment in a certain direction, probably, I can't remember, maybe it's this direction. Well, if it comes into contact with another magnetic field, then it's attracted to that magnetic field because it has its own magnetism, and they interact in such a way that they're attracted to one another. But if you've got another electron here spinning in the other direction, let's see, that direction, then it will produce a magnetic moment in the other direction, and they cancel each other out. So when that happens, they actually repel magnetic field. They're not maintained or retained within the magnetic field. And that's called diamagnetism. So examples of that, oxygen that we've just seen described in this video is paramagnetic because it has unpaired electrons. And diamagnetic elements such as nitrogen, dinitrogen, which has all paired electrons, is diamagnetic. Now, this is not just something we invented, pulled out of thin air. It's observed, and it can be measured in a device that's schematically like this one shown in the slide, where you have a very sensitive balance, and you lower your sample into a magnetic field, and you measure the pull or the repulsion of your sample as it enters that field. And you can determine with proper calibration what that represents for each of the elements, what forces. So if you only have one or two unpaired electrons, you get a certain force, but if you have three or four, you get a stronger force. And that can be calibrated for the number of unpaired electrons. This is what it would look like. On the left-hand side, you see a beaker full of liquid oxygen being poured into the gap between this huge horseshoe magnet. The magnetic field in there is very strong. And some of it spills off, right? But some of it in the right-hand photograph shows you that it's retained in that magnetic field, and it will stay there until it evaporates. Oh, Professor Dave is going to talk to us a minute, and he's going to he's going to rehash some things that we've already learned, but he's also going to say something about that SP mixing. And after this video, we're going to look at SP mixing on our own. So let's let Professor Dave do some talking here. Let's see. There we go.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called SP mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of two atomic orbitals will always result in two molecular orbitals, one bonding and the other antibonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have 2 unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay, that's enough of Professor Dave. This is the diagram he was using. And you'll notice that the breaking line for sp mixing versus no sp mixing is between nitrogen and oxygen. So if you don't understand or have a handle, a firm grasp of why this happens, it's just as important for our purposes to know where it happens. So to the left, nitrogen and dinitrogen, and to the left, notice these are all diatomic molecules, homonuclear diatomic molecules. Nitrogen, and to the left, you have significant sp mixing, which places the pi molecular orbital beneath the sigma molecular orbital. So these are from the 2p's and this is from the 2p's. And then the antibonding for the pi occurs here, and the antibonding for the sigma occurs here. So that's with mixing, sp mixing. If you have no sp mixing, then you will see the diagram that I showed you for difluorine, where we have the sigma down here, and then the pi, and then the pi star, and then the sigma star. So in the no mixing, you have the sigma and the sigma star on the outer regions, and the pi star in the middle. That's the way I remember it. No mixing puts the pi's in the middle. Let's see. Next. There we go. This is another diagram which adds a little bit more information. In fact, it adds electrons in there for the elements. And notice we've got the no mixing on the right, and the breaking line is between nitrogen, dinitrogen, and dioxygen. And it also fills in electrons to illustrate the difference in these different molecules that is attributed to either diamagnetism or paramagnetism. There's oxygen with its unpaired electrons, and there's right here, and there's fluorine with all of its paired electrons is diamagnetic. Nitrogen is diamagnetic, as is carbon, but then boron has unpaired electrons, and it is paramagnetic. And then the bond order is calculated there, and the bond energies are also included. And you'll notice that the single bond, let's see, the single bond here for diboron is a certain value, 159. No, that's the bond, excuse me, that's the bond distance. The bond energy is kilojoules per mole, 290 for diboron, but the single bond energy for fluorine is only 154. So just because they have the same bond order doesn't mean they have exactly the same bond energy. That, in fact, that had to be determined experimentally. But if we had time, we could discuss the significance of the two. My guess is, no, I don't have a good guess. Not right off the top of my head. So let's carry on. Excuse me. Hit the wrong button. Some authors will call this, instead of SP mixing, they'll call it sigma pi mixing. That's because they believe that the mixing, the effect that's felt in this reversing of the sigma and the pi is due to the formation of the molecular orbitals, not to the mixing of the atomic S and Ps. But SP mixing has sort of stuck, and you may hear it both ways. Okay, now what do we do when the atoms are dissimilar? Like for this one, we have carbon monoxide. Let me get that out here. We have carbon monoxide for this one. And if we were to go ahead and draw this with our VSEPR model, we would have 4 electrons. Yeah, 4 and 6, which is 10 electrons. We would have a carbon, oxygen. That's 2, 8, 1, 2, 3, 4, 5, 6, 7, 8. And in order to make an octet here, we would have to maybe take a pair from there and a pair from here, which would make a triple bond, and that would be 2, 4, 6, 8, 2, 4, 6, 8. So this would be our Lewis dot structure for that molecule. Okay, and we could say some things about it. And if we use what we know at this point in time about electronegativities, we would say that the bond is polar for the oxygen, because the oxygen is to the right of carbon. It is more electronegative, and that gives you the estimate of electronegativities and relative electronegativities and the polarity of the bond. But if we go to the molecular orbital theory and draw an energy diagram for that molecule, we find that the oxygen, because it has a higher effective nuclear charge, is going to have the P's and the S orbitals at a lower energy. They're closer to the nucleus because it has more protons. And carbons will be further from the nucleus. So how do they mix then? Well, whenever possible, we try to mix orbitals of the same principal quantum number and the same N and L numbers. So we would try to mix the S's, which we do here, right? The S from the carbon mixes to give you a sigma star and a sigma here from those two, right? So you can see that. And then when we get the P's, we try to form orbitals there. And this is carbon and oxygen. In this case, we have sigma here, and then we have pi. But in this case, it looks like there's no mixing, right? There's no mixing. Okay, so the rule there is that you take the more electronegative element, oxygen more electronegative, and is that in the region of the periodic table where there is no mixing with the homonuclear diatomic? Yes, oxygen has no mixing, whereas carbon would have mixing if there were two carbons. But the oxygen takes precedence because it's more electronegative. And that tells us, by rule of thumb, that the molecular orbital diagram for carbon monoxide has no mixing. That's the way I understand it at this point. Now, a trained chemist who's actually done the calculations and created these models from the mathematical formulas might find errors with that rule of thumb, but for now, that works for me. And then when we put the electrons in there, we find that that we have, let's see, here we go. We have bonding, 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 and only 2 in the anti-bonding. So we have 2, 4, 6, 8 minus 2 is 6 divided by 2 is 3. A bond order of 3 gives us the triple bond. Now we can also surmise polarity from this diagram. Notice that the lower the energy of the atomic orbitals from the beginning brings the overall energy of the diagram down. So these orbitals are closer to the oxygen and further away from the carbon. And that puts more electrons in this region closer to the oxygen, which implies polarity toward the oxygen. All right. So let's see. HF is another possibility for a diatomic, a heteronuclear diatomic molecule. But in this case, we don't have the luxury of mixing similar atomic orbitals to make our molecular orbitals, because hydrogen only has the 1s orbital, whereas fluorine's valence shells are p orbitals. So we have to mix those. And I think on the next slide, yes, we're going to get molecular orbitals that are due to the 1s from the hydrogen, which is at a high level, energy level, and the sigma, the p from the fluorine puts the sigma way down here, very low energy. So this is a fairly strong bond. And that also puts the electrons closer to the original energy level of the fluorine, which says we should have polarity toward the fluorine, which is in fact what we observe. Let's see, I had another thought. And I've lost it. Let me run it back through my head, the discussion. What is 2p, sigma, polarity? Oh, it has to do with the acidity of HF in aqueous solution. In that case, we would call it hydrofluoric acid. This is, we would expect, because fluorine is a halogen and all the other halogens produce strong acids, we would expect this one to be a strong acid, but in fact it is not. It is a weak acid. And since the reaction requires that we ionize the molecule to produce hydrogen ions and fluoride ions, there needs to be enough energy going in to separate them. Well, in fact, the energy that's required to separate them is due to the fact that this very low sigma bond in energy makes it more difficult to raise that energy level to a height that will break the molecule apart. So this extra low energy down here, due to the fact of the fluorine's 2p orbital being low energy, makes it more difficult to break that bond. Right? So that's another way of looking at the acidity, the weak acidity of hydrofluoric acid. Let's see. Okay. This diagram predicts that HF molecules should be stable. Yes. Yes, it does. And they, in fact, are. And you can actually measure. No, we've already done that. Measure the polarity of HF. That occurred in a previous chapter. So I'm not going to hammer that one anymore. Let's see. There we go. If we look at the electron distribution around the molecules, we find that the probability of finding an electron is closer to the fluorine atom than it is to the hydrogen atom. And that also speaks to the polarity of the bond. I'll leave that up there to be recorded, but it's not saying anything new that I haven't already said. Okay, this concept of delocalization. I mentioned earlier that the more delocalization you can introduce into a molecule, the more stable it is. This runs parallel and actually improves upon the concept of resonance. So, for example, remember we had the nitrate polyatomic ion, and we could have drawn it like this, and that, and that, and that. And I'm leaving out the extra unpaired electrons. And it would resonate because of the limitations of the localized electron model. It would resonate with this possibility. Which would also resonate with this possibility. Okay? That's the way we had to describe it with a localized electron model, because we had no other way to describe these bonds. But we know from measurements that each one of these bonds is exactly the same energy and the same length, which means they are identical bonds. Now we have the ability, this is one way of looking at it, we have the ability to express these bonds in terms of bond order. So the bond order for these bonds is going to be somewhere between 1 and 2, right? So for simplicity's sake, each one of these is 1.5 bond order. And I expressed that at an earlier stage like this. We just put dots on the side and dots on the side. So it's not a single bond, it's not a double bond. It's in the middle. The other explanation is that you have sigma bonds here, molecular orbitals, sigmas, and then there are unused pi orbitals, p orbitals that form pi bonds, but they don't form complete bonds at any one location. what happens is the electrons that go into the pi bond system are delocalized over the entire molecule. And that delocalization is responsible for the stability of that ion and the stability of many other examples that use this delocalizing pi bonding. I think I've got another one to show you in just a second. Yes, in fact, the very next slide. This molecule is called benzene. Benzene has been identified as a fairly significant carcinogen. So its use is limited and regulated. But for our purposes, we don't have to deal with it. We can just look at its structure. So the benzene molecule, if we draw it with the localized electron model, we have to draw it with these double bonds and single bonds in place and resonate between the two possibilities. Notice that all we have to do is just take all the bonds and rotate them by one position. And if you rotate them again, then you get the one that you just used. So there are really only two unique Lewis structures for these this molecule in these two forms that resonate. Well, the fact of the matter is, we have these sigma bonds between each of the carbons. And when we draw organic molecules, for simplicity's sake, wherever two lines meet, those lines are bonds, then we assume that there's a carbon there. And actually, we don't draw in the hydrogens either, typically, but in this case, the hydrogens are there. What that means is that if we have a hydrogen here in these two bonds, we have 1, 2, 3 groups, which, according to our hybrid orbital theory, says that it's sp2 mixing. It's trigonal planar. This whole molecule exists in a single plane. But that leaves unused p orbitals. So that's where we get a double bond here and a double bond there and a double bond there. But that's where the localized electron model falls on its face. It cannot adequately describe the reality that each one of these bonds is equivalent to the other. So what we have to invoke now is, with our delocalizing effect, we get a pi bond system around the entire molecule. And the molecular orbital model just actually, it sort of ignores that, right? This would be a way to explain it with a localized electron model if we had a pi bonding system. But the delocalizing itself is what accounts for the stability of the benzene molecule. Anywhere in nature where you have a benzene type ring, and it expands to other types of molecules. They can have nitrogen in them, they can have sulfur in them. If they have these delocalized pi structures here, and that relates to a concept called aromaticity. If they are truly aromatic, then they have that pi bond system, and it makes them very stable. So in nature, when you have organic molecules that are created by this plant or that fungi or whatever the case may be, when the plant dies, then these molecules are recycled back into nature so other plants can use them, or other fungi can use them, or other bacteria, whatever the case. But as they're being broken down, it's easier to break down the side chains and those molecules that do not have this stabilizing pi system. So the very last molecules that are ever attacked in nature to degrade them are the pi bonded systems, the aromatics. They are extremely stable. And this is another way of looking at them. With our localized electron model, with hybridization as a modifier. So there's your 6-carbon ring and the sp2 hybridization. And then I think the next one, yes, shows that those unused p orbitals then enter into a pi system. And the concepts that are inherent to molecular orbitals, which involves a description for the entire molecule for electron locations in the bonding systems, lends itself to allow those pi's to overlap in a system rather than individuals, where you have individual double bonds here, here, and here. Then this system concept that is derived from the molecular orbital model allows us to make this prediction and explain why these particular types of molecules are extremely stable, this delocalizing effect. This is the nitrate ion. I only kept this one because it had a nice little picture in it. The video that goes along with it doesn't work anymore because flash is out the window. Not supported anymore. This last slide describes a method for actually measuring the energy levels in a molecular orbital system. And it's based upon, actually, it goes back as far as the photoelectric effect. In the photoelectric effect, when you've got usually a metallic atom, and you've got electrons in these orbitals, in the outermost orbital, the question is, what frequency of light will eject that electron? Will take it to infinity, from there to infinity. So you have to have just the right amount of energy. Just the right amount of energy to eject that electron. Now, a minimum amount of energy is required, right? So light, say of red light for a particular element would not eject an electron. But if you get down toward the blue range, each photon has enough energy to eject an electron. Now, it takes only a certain amount of energy to get that electron to leave the atom. And then any extra energy is translated into kinetic energy. And that kinetic energy can be measured for the electrons when they leave, right? Detectors can tell you what the energy of that electron is. Okay, so the amount of energy that comes in from the light is this factor, right? And that's, this is Planck's constant, and that's the frequency, right? I think we looked at that earlier. So that total amount of energy that comes in with the photon, some of that is required to remove the electron. That's called the work function. So a certain amount of energy is required, and then the rest of it is translated into kinetic energy. Okay? So if we measure the kinetic energy, and we know, based upon the frequency of the light that we use, that value, we can calculate the work function. And the work function tells us where that electron is located in terms of energy. And this particular diagram is a trace that shows us the energy levels for each of the orbitals. Now, this can be used for atoms, right? We can do this photoelectron spectroscopy to determine the energy of the, actually measure the energy of the various orbitals. But it can also be used for molecules. And in this case, we've done it for some molecule. It doesn't say which one it is, but it also tells us what are the molecular orbital energy levels. And the equations that predict the energy levels for these molecular orbitals agree with the actual measured values. That's the whole point of this slide. The theory matches with the experimental evidence. Okay, that's it for your chapter 9.4 to 9.8 in Brown. And this is the material that we'll cover in the upcoming exam.